Hi everyone, let's continue from finding limits graphically to finding limits numerically, which basically means finding limits by plugging in numbers. We're also going to continue to connect the idea of continuity to the idea of limits as we work through this. And the first example is a great example of that. This is the limit of a quadratic function. So we're thinking about the function y equals 2x squared plus 1. And we would like to know what happens to our y values when x is very, very close to 5. So in this case, I know a fair amount about this function. It's a parabola. It's been stretched vertically by a factor of 2 and shifted up 1. So it's kind of a tall, skinny parabola going something like that. That's very rough, but that gives us the idea. What's important here is that I know that quadratic functions are always continuous. They don't have discontinuities. And assuming that the function is continuous, the value of the limit will be the same as the y value at the point where x equals 5. I'll write this down a little more formally when we flip the focus from the limits to the continuity, but that in general is true. If the function is continuous, the y value at the point will match the value of the limit. So here, what I'm saying is that if I want to know what my y values are getting close to, I can just plug in 5 and find out the y value right at that point, and that will be the y that we're approaching. So I'm seeing 2 times 25, which is 50, and then when I add 1, I get 51. So if you are confident about the function that you're working with, you know that it's a nice continuous function, you can absolutely at that point just plug in the x value. But don't default to that being always what a limit means. There would be no reason for limits if all we needed to do was find f of 5 every time. All right, let's look at another one. So now I'm getting something a little bit more interesting. It's a fraction. I want to know when h is really close to 0. So I'm thinking tiny numbers like negative 0.001 and positive 0.0001 and so on. I would like to know what happens to e to the h minus 1 over h. And this is actually one that's interesting later on in the quarter, but we probably won't remember it then. This is really just going to be a technology question for us and a question about understanding how to build your table. So this is similar to when we were trying to find instantaneous rates of change. We wanted to make intervals that were smaller and smaller and smaller. Here, we want to find h values that are closer and closer and closer to whatever value we're really interested in, which is 0. So this 0 sitting in the middle of the table is not by accident. That should be there. And we should be filling in h values that are getting closer and closer to 0 on the left and closer to 0 on the right. So for example, I could do negative 0.5, negative 0.1, negative 0.01. And what I would say is just go for what you think looks like a fairly good pattern of getting closer. And if it turns out you're not seeing a good enough pattern, maybe you need to pick values even closer and we'll just redo our table if that's the case. But generally getting down into the hundredths place, you're going to get a pretty good idea for the purposes of the estimating that we're doing. You do not have to use the exact same values on the left and right, but I'm trying to build a pattern, so it seems like not a terrible idea. From here, we're just going to plug this into a calculator. So I'm going to pull up Desmos, and I typed it in using function notation just so I can get them quickly. You could also just set this up and then change your h value, but I'm going to say I would like to know what happens when I plug in negative 0.5. And when I plug in negative 0.1, and when I plug in negative 0.01. So that is the left-hand side. And here, if we want, we can even check f of 0, but it is in fact undefined because we end up dividing by 0. On the other side, I just chose to use the positive versions of those same numbers. Oh, except I think I went a little further this time. There we go. Okay, so if I'm looking for a pattern, so for homework purposes or your notes, you can copy these in, but I'm just going to look at the table right here. So my y values were 0.787-ish, and then they increased to 0.95. And then as we got even closer, they increased to 0.995. That's getting really close to 1. So right now I'm thinking maybe my y's are approaching 1. On the right-hand side, when I'm a half a unit out, I get a y value of 1.297. And then as I get a little closer, it moves down to 1.05. And as I move even closer, it gives me 1.005, which again appears to be approaching 1. So I think from my numerical estimation that my limit is 1. My y values are getting close to 1 as my x values get close to 0. So for evidence of this, you would just jot down your table, and I am going to be lazy and just let you look at my Desmos table, but I will say that the value of the limit is 1. All right, I'd love for you to pause and try to at least set up the table for the next one. If you want to take a moment to go to Desmos or Technology and find the values and decide what you think the limit is, that's great as well, but the setting up the table is kind of the key step here. Once you've done that, we can look at it together. So what's really important here is that this time we're looking for the limit as y approaches 1. So when I set up my table, what goes in the middle of the table is 1. And that means that I'm not going to pick small negative and small positive values to plug in here. I'm going to pick values just smaller than 1 and just bigger than 1. So for example, approaching from the left, I could start at 1/2. That's great again, but then I would want to go up to 0.9 and maybe up again to 0.99. On the other side, I'd maybe want to start at 1.5 and work my way in. So then I'd say, okay, well, let's drop it down to 1.1 and then down to 1.01. So that is how I would set up a table, a starting point for this one. So let's go to Technology again. And I did some of this setup so that you wouldn't have to watch me type at all. Note that I did switch from y's to x's. The table would work fine either way, but if you use y as your independent variable, Desmos flips this graph across y equals x basically. It makes it go up the y-axis instead. It actually uses y as your y value. So if you want to actually see the graph, you'll have to give that x instead of y. Okay, so here is exactly what I said I wanted to do on paper, and I see my y values going from 0 to -30 to -31.55, and on the right I see them going from 0, interestingly again, to -27, 28-ish, to -31.23. So really, I think I have a pretty good pattern. It's somewhere between these two, I imagine. One possibility would be to just average the -31.55 and the -31.24-ish. You could also, if you want, just go a little bit closer. So back on the paper, maybe we would move everything in one step and go 0.9, 0.99, 0.999, and 0.1, 0.01, 0.001. So here I've gotten it to at least agree to one decimal place. So I would say -31.4 is a reasonable estimate of what this value is. Basically, it appears that we're not getting a nice integer value, and we shouldn't expect to always get nice integer values, especially not when we're working with trig functions and weird exponential functions. So I would say -31.4 is a good answer. I didn't really look at the graph last time, but let's look at it this time. Can I see it? I'm interested. Ooh, it's way down here. Okay, so I'm interested in what's happening when x equals -1. It looks like that's right at the bottom of this, so we can follow this down. And here, let's click on it. Oh, it's not quite right at the bottom. It's very close. It's just over from that. I don't know if I can drag it there. But you can kind of do the same thing graphically by dragging this around. 9, 6. There. Didn't go quite far enough. So somewhere around here. Oh, one undefined, there it is. Okay, so you can play around a little and make sure it matches what you're seeing in your table. So you can use Technology and look graphically as well. All right, so back in here, again, the work you would show me is to just fill in the table that you used and then say that the value you're seeing is about -31.4. All right, so that's how we find limits numerically. It can be slightly tedious, but use technology. This is nothing you have to crunch on your own. And also remember that if the function is continuous, you don't even need to make the table. You can just plug in that x value. It's when plugging in the value gets us stuck. So if you'll remember, we got undefined here and undefined here, so we can't actually get a y value, and that's when limits get really interesting, when there's no y value there, but you still want to know what's happening nearby. All right, thanks for watching.